Hello everyone. So welcome to our new video on uses or applications of influence line diagram. And this topic is for simply supported beam. That means using influence line diagram for shear force and bending moment, we can find out the shear force and bending moment at any section by using the influence line diagram of that section. Okay. So here is a simply supported beam and A and B are the simply supported ends of the beam, and it carries some point loads such as W1, W2, W3 and W4. So using influence line diagram for shear force and bending moment at a section, shear force and bending moment at that section for any given loadings can be found easily. So as we already know how to draw the influence line diagram for shear force and bending moment at a particular point. So this is a particular point C, and we have to draw the influence line diagram for the shear force at the point C. For that, this will be the influence line diagram, and this ordinate will be Z by L and this will be L minus Z by L, and the remaining ordinates are Y1, Y2, Y3 and Y4. Okay. And come to this figure, that is the influence line diagram for bending moment at C. Okay, and this is the maximum ordinate, that's called YC, and its value is Z into L minus Z by L. Okay, and Y1, Y2, Y3, Y4 are the other ordinates corresponding to the load W1, W2, W3 and W4. Okay, then what about Z? Z is the distance of the considering point. That means in this case we are finding the shear force at C. That means the distance from the starting point to the finding point C is the Z. Okay. So these are the values, and first of all we need to draw the influence line diagram for the shear force and also for bending moment, and by using these ordinates, that means L minus Z by L and Z by L, find out the other ordinates Y1, Y2, Y3, Y4 corresponding to the loads W1, W2, W3, W4 for shear force diagram, for shear force. Then for bending moment, draw this influence line diagram, and by using this maximum ordinate value, that means Z into L minus Z by L value, find out the other ordinates Y1, Y2, Y3, Y4 by using the properties of similar triangles. Okay. Then the figure shows a simply supported beam subjected to 4 point loads W1, W2, W3 and W4. Okay. Let Y1, Y2, Y3 and Y4 be the ordinates of influence line diagram for shear force at the section C, and let capital Y1, Y2, Y3 and Y4 be the ordinates of influence line diagram for the bending moment at C. Then how will you obtain the shear force value at the point C? That's equal to W1 Y1 plus W2 Y2 plus W3 Y3 plus W4 Y4. Here the W1, W2 and W3, W4 are the point loads. So the corresponding point loads into corresponding ordinates will give the shear force value at that point. Okay, it is from the influence line diagram for the shear force. Then from the influence line diagram of bending moment, we will get the maximum, we will get the moment value at the point C. How? It is W1 into capital Y1, W1 into capital Y1 plus W2 into capital Y2 plus W3 into capital Y3 plus W4 into capital Y4. That means we have to multiply the load into corresponding ordinate. Here we are finding this YC value to get the other ordinates. Okay, and also here we are using the L minus Z by L and Z by L value to get the ordinates Y1, Y2, Y3 and Y4. To find out the influence line diagram, to get the shear force value and bending moment, just draw the influence line diagram and just multiply the loads and the corresponding ordinates. Okay, for both shear force and bending moment in case of point loads. Okay. In case of UDL, that means simply supported beam with UDL of intensity W per meter is acting on a beam. Consider an element of length dx on this UDL of intensity W per meter. Let x1 be the starting point of this UDL and x2 be the ending point of this UDL from the initial point. So this is the influence line diagram for the shear force at C, and this is the influence line diagram for the bending moment at C. Okay. In the previous case, we are provided with a point load, so that we just multiply the point load into corresponding ordinate. Here we have to multiply, or here we have to multiply the intensity of load into the area of shaded portion. Here you can see that the one of its portion in the positive direction and the other one is in the negative direction. So take this one as positive and this one as negative. Okay, this one is positive and this one is negative. Coming to this, all direction is positive. Okay. So while considering the influence line diagram for shear force at C, we need to find out, okay, listen here, shear force at C due to the elemental load W is equal to W dx into Y, where Y is the ordinate. Then shear force at C due to UDL from W1 to from H1 to H2. Here we considered an elemental length dx only. Then we have to find it out for the entire length h1 to h2, which is equal to integral h1 h2 w dx into y. That means w into area of shaded portion in influence line diagram for the shear force. Similarly, bending moment at C due to the UDL is equal to w into area of shaded portion in influence line diagram for MC. Okay. So simply we can say that if you are if you have to find out the shear force value at a particular point C for a UDL, we just need to multiply the intensity of load, that means W, into area of the shaded portion. So here you can see a parallelogram. For that, how will you find the area, which is equal to half into h into a plus b. So a and b are the parallel side and h is the lengthwise side. So half into h into a plus b will give the area of this shaded portion. Similarly, find out the areas of these portions. Okay, so this is a method to find out the shear force and bending moment value for a UDL loading. Thank you.